The closest star to Earth beyond our own sun is so far away that if you drove there at highway speed, the journey would take longer than the universe has existed. And yet, we keep looking at it. Proxima Centauri, 4.2 light-years away. A tiny red dot that most people have never heard of. And the question is simple, almost childlike. Could we ever actually go there? Not in a movie, not in a thought experiment, but for real, with engines, with physics, with human beings or machines making that crossing. The answer is not no. But it is one of the strangest, most humbling stories in all of science. Let us start with some perspective. Right now, the fastest human-made object ever launched is Voyager 1. It has been flying since 1977. It left our solar system entirely, and by any measure, it is the furthest thing we have ever sent into space. Its speed is roughly 61,000 kilometers per hour. That sounds extraordinary, and it is, for us here in our little corner of the solar system. But at that speed, to reach Proxima Centauri, Voyager 1 would need approximately 73,000 years. 73,000 years. Anatomically modern humans have only existed for around 300,000 years. Agriculture is about 12,000 years old. The entirety of recorded history fits inside 10,000 years. And we are talking about one star. The nearest one. So the question is not just can we build a rocket? The question is can we build something so fundamentally different from anything we have ever made that it collapses that 73,000 years into something a civilization might actually attempt? Here is why this is so hard. Space is not just big. It is patient. It does not care how clever you are. The tyranny of distance is absolute, and the only way to fight it is speed. Chemical rockets, the kind that sent humans to the moon, burn fuel to create thrust. They are extraordinary machines. They are also, in the context of interstellar travel, laughably slow, like trying to cross the Pacific Ocean by swimming. To reach even 1% of the speed of light, you would need an almost incomprehensible amount of fuel. And here is the cruel joke of rocketry. The more fuel you carry, the heavier the ship, the more fuel you need to move that fuel. It spirals out of control almost immediately. So engineers and physicists have been dreaming up alternatives for decades, and drives use electric fields to accelerate charged particles out of the back of a spacecraft. They are incredibly efficient. Missions like Dawn and Hayabusa have used them. But they produce very gentle thrust. They are more like a long, patient push than an explosion, still far too slow for interstellar distances in any reasonable time frame. Nuclear pulse propulsion, sometimes called Project Orion, proposed detonating nuclear bombs behind a ship to push it forward. In the 1960s, engineers actually worked on this seriously. It could theoretically reach a few percent of the speed of light. But it was abandoned for obvious reasons. Nuclear explosions in space raise certain complications. Then there is nuclear fusion. Instead of splitting atoms, you fuse them together. The same process that powers the sun. A fusion drive could theoretically be far more efficient than anything we have built. Several serious proposals exist, including one called Project Daedalus from the 1970s. The problem is that we still cannot sustain a controlled fusion reaction here on Earth. We have been 50 years away from fusion for about 50 years. None of these get us there quickly. But then, in the 21st century, a different idea started getting serious attention. What if you did not carry fuel at all? That is the idea behind laser propulsion and light sails. Photons, particles of light, carry momentum. Very small amounts of it. But if you make a sail thin enough and shine enough laser light at it, you can push a small spacecraft to extraordinary speeds. In 2016, a project called Breakthrough Starshot was announced with exactly this goal. The concept: build a fleet of tiny spacecraft about the size of a postage stamp, attach a thin reflective sail, and fire a massive array of ground-based lasers at them for a few minutes. The result, in theory, is acceleration to 20% of the speed of light. 20% of the speed of light. At that speed, you reach Proxima Centauri in roughly 20 years. 20 years is not a human lifetime. It is a long time. But it is imaginable. It is the kind of timescale a civilization could plan around. Of course, the challenges are enormous. The laser array would need to output more power than most countries currently produce. The spacecraft would have to survive interstellar dust particles hitting it at a fifth of the speed of light, each one like a tiny bullet. And when it arrives, there is no way to slow down. It would streak through the Proxima Centauri system in hours, snapping photos and beaming data back. Data that would take 4 years to reach us. At the speed of light. Now, all of the above is about sending machines. Tiny ones, sending human beings, is a different category of problem entirely. A crewed ship would need to be large enough to sustain life. It would need food, water, air, radiation shielding. The interstellar medium is full of cosmic rays, high-energy particles that slowly damage DNA. A journey of decades would require solving problems in medicine, psychology, and engineering that we have barely begun to think about. There is also the simple human problem of time. Even at 20% of light speed, if we could somehow send a crewed ship that fast, which we currently cannot, the journey takes 20 years. The crew that arrives would not be the crew that left. Children born on the ship would grow up never having known Earth. The people who built the mission would be old or gone. Some theorists have proposed generation ships, massive vessels where multiple generations live and die during the crossing. The people who land would be the descendants of the people who launched. Others have proposed something that sounds like science fiction but is taken seriously by some physicists. Suspended animation, or some form of induced hibernation, where the crew sleeps through the journey and wakes up at the destination. And then there is the question that no one fully knows how to answer. What happens to the human mind, cut off from everyone and everything it has ever known? In the dark, for decades. Here is what makes all of this feel urgent. In 2016, astronomers discovered a planet orbiting Proxima Centauri. It sits in the habitable zone, the range of distances from a star where liquid water could exist on a surface. We do not know if it has an atmosphere. We do not know if it has water. We do not know if it is anything other than a barren rock. But it is there. And it is 4.2 light-years away. If that planet has even a trace of life, microbial, ancient, vanished, it would be the most important discovery in human history. It would mean we are not alone. It would mean life is not a miracle unique to Earth. It would reshape everything. And the only way to know for certain is to go. So where does this leave us? Breakthrough Starshot is real funding and real research, but the engineering challenges are generational. We are probably not launching anything at 20% of light speed in the next 20 years. More likely 50. Possibly 100. Fusion propulsion remains dependent on solving fusion, which may happen in the next decade or may not. Crewed interstellar travel, by almost every serious estimate, is centuries away. Not decades. Centuries. And yet, humans were not supposed to leave their continent. Then they were not supposed to cross the ocean. Then they were not supposed to leave the atmosphere. Then they were not supposed to walk on the moon. Every one of those barriers fell because a generation decided the question was worth answering and started building toward an answer they would never live to see. So, could we ever travel to another star? Yes. Probably. Not soon. Not easily. Maybe not with human bodies at first. Maybe with tiny machines, then with bigger ones. Then eventually with crews of people who were born into a civilization that had already decided it was going to happen. The honest answer is that the physics does not say no, and in the long game of human ambition, that has always been enough to eventually get us there. Proxima Centauri is not going anywhere, and neither, it seems, is our need to reach it. If you want to understand more about the universe that is waiting for us out there, subscribe. There is a lot more to cover. Next time, the planet that might actually support life, and what we would need to survive on it.